Hello, everyone. Another exciting day, another exciting lecture. Right on?
Better be.
Well, we started the week with gluons, we went with quarks, and today we're going to go a little into this standard model, which is the standard model of quantum mechanics. Okay? So, what is it? Well, before we can get there, let's do a very, very brief history. And what I want you to look at the similitude, how these things compare, and they're so much alike that it's stunning. It's scary more than stunning. You've heard about Ptolemy, right? He wrote a book called the Almagest. And
What?
Almagest.
Almagest.
Almagest. And he wrote it, 2,000 years ago. And he wasn't the only one. There were other people, Hipparchus. There were several people who, in fact, that theory, his way of looking at the world, lasted all the way till the days of Galileo in the 17th century. And so it's important to know that, first of all, these guys were mathematicians. If you look at Ptolemy, all he did was calculations. He did observation and calculation. And what did he conclude? Well, he ended up with a very incongruous system that we finally ditched completely. And it was made of epicycles and so on. And what was the big problem? Well, there were several problems, but the big problem that they were trying to figure out, why was Mars going backwards? What was this retrograde motion? How could we explain that? What was going on in the heavens there?
What's wrong with Mars?
There's retrograde motion. I'll show it. Let me give you a. This is a.
This is the first time I've heard this. Mars is.
Yeah, is a serious problem, Mars, because it kept going backwards. You know, it would go forward in time in the sky, and you would see it go in one direction, and then suddenly it started going backwards. You say, how can I explain that? They tried to explain it, and they came up with a system of epicycles. And here it is. Here's a graphic of it. Let's see if I can move this over here. The blue dot on the left, the 1, 2, 3, 4, 5, the blue dots are the Earth, and the red dots are, of course, the red planet Mars. And as you can see, the Earth, because it's closer to the sun, it overtakes Mars. So when it's catching up to Mars, like at 1 and 2, Mars is still in front. But when it overtakes Mars and it's at 4 and 5, then Mars is going backwards. See what's happening? We go faster.
What?
And they had to explain that in the sky. They were just looking at the sky and they say, look, Mars is going forward and now it's going backwards. How do we explain this? And so what they did was they put Earth at the center of the universe. And that's the Ptolemaic system. And here it is. You'll get a picture here, a little video of how Mars and the moon, you know, how they figured this in their notion of how the universe runs, how it works. And as you can see, the Earth is at the center. And in fact, it's not at the center. They put it off center because they realized that the moon and other things had elliptical kind of motion, wasn't perfectly circular. And so they had to offset the Earth. And they offset the Earth a little bit, and you'll see it there in a second. The Earth is moved off center. Right there. You see it, it's off center. And the planets, such as Mars, instead of being rolling around the sun, they had it rolling around the Earth. And they had to put these epicycles. Epicycle is a circle within a circle. That's what an epicycle means. And so they had, you know, it's like the cowboy who twirls around his head a rope, the lasso. And that's more or less what this was like. The Earth was at the center, standing still. Obviously, the Earth didn't move. The gods made it that way. And Mars was twirling around the Earth, and so the explanation was that retroactive motion was due to the fact that the cowboy was twirling his rope around his head, and so it got very complex after a while because they knew at least of 5 planets. Okay, they were aware of 5 planets, and this is what it looks like. This is how complex the system of epicycles became. It just became so unmanageable because they had to create one epicycle per planet. They had to explain each one separately. And they said, well, how do we explain this one? Well, I explain this one this way. How do you explain that one? Well, I need another equation for that one. And so they had different epicycles for each one of these different planets. And they had different cowboys with different lassos over their heads. And it was just so cumbersome, so complicated, until they got to the days of Galileo, when they started questioning Copernicus first, right? When they started questioning whether the Earth was really the center of the universe. And it was there that people like Kepler were able to go in there and say, no, look, not only do we go around the sun, but we go around the sun not in circles, we go around the sun in ellipses. And he came up with Kepler's laws, which later Newton was able to put in mathematical form in his equations. Okay? Why am I bringing this up? Because what you're staring at right there is the particle model of quantum mechanics. The cumbersome, the Ptolemaic system that we have today for the standard model. Here's the standard model. Okay, I presented it yesterday. It looks like that. Very pretty. You have the quarks up the upper left-hand corner, the violet balls. You have then a series of particles on the right hand. They're orange, up and down, the bosons. And then you have all these other green ones, the electron, muon, and tau, and so on, called the leptons. So we have quarks, we have leptons, we have bosons, and then we have a scalar boson, because we have subcategories of categories and subcategories of those as well. And you say, well, hold it, how many particles do we have in this system? And here's the number. We have a total of 17 particles. These are the fundamental particles. That's what they're called right now. And they're not really fundamental, but we have no other name for them, so we call them the fundamental particles, or forces, because they're not really particles, they're forces, as we discussed this yesterday a little bit, and I'll go over that. If I have time today, I'll cover that as well. But here you have the quarks. You have the up, the down, the charm, the strange, the top, and the bottom. So they gave them all these names. They have different properties, charge, spin, and other flavor, and so on, color. We have the leptons, and we have the electron, muon, tau, electron, neutrino, the muon, neutrino, and the tau neutrino. So they're essentially the neutrino family. And then we have the gauge bosons, and those are the gluon, photon, the Z boson, the W boson, and the Higgs boson, which is a gauge boson, by the way. So they have all these categories. So what are these categories? What do they mean? What are we talking about here? Well, here's a lepton. Here's the definition. A lepton is an elementary particle of half integer spin. Spin half. Blah, 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 blah. Whatever go. And it doesn't undergo a strong interaction.
Half integer spin sounds like not turning 360 degrees. Or just like 90 degrees.
180 degrees. Is that what
they're talking about?
Not really. That's not what they're talking. See, well, I guess I got to go into spin because my son is going to kill me if I don't tell him the answer now. That was the punchline, but he wants it now, so I have to give him the spin now. Okay, what is spin? Let's go in there so that you can keep this in mind as we go along. This is spin. They don't know what spin is, essentially, and here it is. Here's the definition. Spin is an intrinsic form. It's a kind of angular momentum. I thought angular momentum was angular momentum. No, this is a form, a type of angular momentum carried by elementary particles, composite particles, hadrons, and atomic nuclei.
Wait, what do they mean by angular momentum now?
Well, angular momentum is a like circular curve, like
Not
the
straight.
Earth. No, it's
Anything
like the
that
Earth
isn't
going
straight.
around the sun.
Don't they just mean any itinerary that isn't straight?
In a way, you could say that. What it is it's a curvature, a curvilinear motion. Think of it, rectilinear, curvilinear. Okay, it's a kind of but let's continue so you can see what it really is, so that you get the handle on spin. You really need to understand spin if you understand these particles. So in a way, he's right. We should say this up front. Spin is one of two types of angular momentum in quantum mechanics. So they had to invent a new kind of angular momentum. The other being orbital angular momentum, which is the normal angular momentum that ordinary sane human beings talk about. Angular momentum is angular momentum, which is the orbital angular momentum, which is curvilinear motion.
Well, I don't know why they call it orbital, but...
Well, orbital because it's curvilinear motion, because it's orbiting like in an elliptical or circular way.
Orbiting something. Like,
correct.
That's a weird way of thinking about it. When I throw a curveball, I'm not imagining a thing that it's orbiting around.
Right, but you got to think of, and you're right about that, but you got to think about it as, maybe epicycle, the cowboy with a rope around his neck, head, not his neck, hopefully. Or you got to think about it as the orbit of the Earth around the sun. That's why they call it orbital, because it's what everybody understands by angular momentum. But for spin, they had to invent something new. And they said, look, the orbital angular momentum operator is the quantum mechanical counterpart to the classical angular momentum. Classical means rational. They had to invent these new types of angular momentum to try to figure out what spin is. And appears when there is periodic structure to its wave function as the angle varies. So now they get into wave function. You're moving wave functions. You're not moving particles. You're talking about wave function. You're talking about moving equations from here to there. Okay, keep that in mind. But look at this. In some ways, spin is like a vector quantity. What the hell? We went from physics motion to vector quantity.
Like 3 vectors.
Yeah, it's a vector. It's a number. It's a value. It's an amount.
But it's a number of directions.
Don't try to explain it. Don't try to even visualize this. It's just a number that these guys use, and they say, what are we going to call that? Well, it's kind of like a motion. It's like a orbital motion. It's like angular momentum. It's like an orientation, a direction. Let's call it spin. And they use the word spin for this, and everybody says, oh, I know what spin is. It's what a top does. Yeah. No, this is not. This is not anything even like it. That's why they say it's like a vector quantity.
I don't even know what to ask.
yeah, we don't even know what to... No, of course.
I don't even know what to ask.
It has a definite magnitude.
At this point, this is the point where I just go, man, this guy's smart.
Yeah, and you go off on the...
way over my head.
And you go and get your lunch, right? It has a definite magnitude and it has a direction. So that's why it's a vector, because it has magnitude and direction, which are the two.
Like a vector, yeah.
Right. And so they're talking about direction. They're talking about orientation. They're talking about pointing in it. They're not talking about motion. They're talking about this thing is static. It's a top.
Orientation.
It's a top. This is the best way to explain it. Imagine that you put a. Let's put ourselves back in here. Imagine that you have an apple. That's the best way to look at spin. You have an apple, and you make a cut on the apple. You make a mark. You cut it with a knife, okay? Okay, so you come one day from one door, and you see the line that you made, the cut that you made, the cut mark on the apple, and you see it from this angle. You say, that has spin half. You just give it a name. That's spin half. The other day, you come from the other side, and you see the line in a different direction. You say, that's a full spin. That's spin 1. The other day, you find it in the opposite direction, 180 degrees. You say, that's spin minus 1. And when you find it on the other side, you say, that's spin minus half. That's the best way to conceptualize. It's not rotation. It's orientation when you measure the orientation of the particle. That's kind of like what they're talking about.
Okay.
They call that spin. That's why they have trouble defining it. They say it's like a vector. It's a magnitude with direction. What do you mean? I mean, spin is spin, right? You take the top, you spin it, right? No, that's not what it is. It's a mark that you see, or the orientation of the particle as they, these guys, how do they come up with this? They accelerate the particle, or so they think, on an accelerator, right? They smash them inside the chamber, and now they see some squiggly thing come out of there, and they say, that's the trace of the particle. And so the particle has a counterclockwise versus clockwise direction. That's a half spin, and that's positive spin. That's one spin and minus half spin, and so on down the line. They give it names to what they see in the chambers. And that's why they can't really talk to you about motion. And it's they're looking at the orientation of the particle when they look at a specific snapshot of it. They look at the mark of the apple in a sense.
In the game programming language that I use, they use the language quaternion when they're talking about the orientation of the object. When you put in quaternion, because I mean, it's not really spin, but they also use orientation because the object has location and it has what do you call it, like tilt or angle.
Yeah. That's what it is. It's kind of like a tilt and angle. One is at 90 degrees to the other, so they say, oh, that's got a minus half spin, and you say, oh, it's spinning. How can it spin halfway?
Spin is halfway. Spin.
You know, can you imagine twirling your top and the top just stops halfway and say, oh, okay, that's got half spin.
That's called turning and not spinning. But what's this got to do with the particles now?
Okay, because they're gonna categorize particles, right? By their spin, by their charge, by their color, by their flavor, and we need to get a handle on what all these things mean. Okay, so let's go. That was spin. I wasn't supposed to present spin, but my son twisted my arm. So we know what a lepton is right now, right? Correct? Okay, a lepton. Again, let's look at the lepton. I gotta make this bigger so I can read it.
What is a lepton?
A lepton is an elementary particle of half integer spin. In other words, spin half.
Does that also count negative spin half?
I'm not sure. I think it does.
Now we're on to the tough questions.
Oh no, the half spin I think are the antiparticles.
Oh, the negative half.
Yeah.
As soon as you put a negative, it's.
Yeah. So this one does not undergo strong interactions. Okay, that means it doesn't pull. Two main classes of leptons exist. Charged leptons. There's charged leptons, also known as electron-like leptons, and neutral leptons, better known as neutrinos. Charged leptons can combine with other particles to form various composite particles, such as atoms and positronium.
That sounds like a cool word.
Yeah, positronium.
That's a nice word. We got to use that word.
Yeah, did you go buy the positronium today? It looks radioactive. It sounds radioactive.
Positronium. That sounds like something from like a Marvel movie.
I'm wondering if there's a negatronium, a negative rhodium, or whatever. While neutrinos rarely interact with anything and are consequently rarely observed. In other words, rarely means they never have observed it because they never see any other particles. But they're talking about, they're saying this thing doesn't interact. In other words, it can't be detected. And so they're hypothetical in a way, but they've proven them. And so these are already, the neutrinos are already part of the standard model. And again, we started with 17 particles, but you'll see that it gets a little more complicated than that. Okay, those are the leptons. Let's go with the bosons, which are kind of like a parallel group of particles.
Wait, real quick. Leptons, bosons, and all these, they're particles, but they're talking about parts of atoms.
Sometimes they're talking about elementary particles. You'll see. Some of these are elementary, some are not. Some are composite.
But what does that mean, element? Just it's.
Well, they don't know because when they say elementary, they cheat on that as well. An elementary particle supposedly is one not made of parts, not made of more basic parts. Yeah, but then they say, give us more money so we can smash it and find out what it's made of. And that's where, it's like an endless game. They say, we just need a bigger accelerator, more energy to smash that little electron, find out what it is made of.
Okay, but so some of these are, or all of them are parts of an atom? That's the way.
Yeah, all these are inside the atom.
Okay, that's
all of this are components of the, and that's important because you'll see why it's important. Boson is a particle that follows Bose-Einstein statistics. So if it follows that statistics, then it's called a boson, okay? Examples of bosons include fundamental particles, see, fundamental or elementary synonym, such as photons, gluons, the W and Z bosons, which are the force-carrying gauge bosons of the Standard Model, the recently discovered Higgs boson, and the hypothetical graviton of quantum gravity. They haven't proven the graviton. They've proven all the rest, but they haven't proven the graviton. They can't make the graviton work, essentially. And so they don't talk too much about the graviton.
Okay, so leptons are half-spin particles, and bosons are particles that follow Bose-Einstein statistics?
Yeah, in other words, well, there's this. They do statistics on these particles. They say, okay, they run one experiment, they run another one, they take measurement, they do these statistics. If it follows certain statistics based on the Bose-Einstein equation, then it's going to be categorized as a boson.
Okay, so they look at a particle and say, okay, what characteristics does this...
Yeah, because we're going to compare this against the fermions, which are the next ones. Okay, so you're going to see there's a contrast. This one follows the Bose or boson Einstein statistics, okay? And some composite particles are also bosons, such as mesons and stable nuclei of even mass number, such as deuterium, which is hydrogen with one neutron in it. Yeah, there it is. And helium and Cooper pairs and so on. Plasmons and phonons, because we have so many particles out there.
Quasi-particles.
Oh yeah, quasi-particle is a particle that is between a concept and an object.
Oh, come on.
It hasn't become yet a...
Okay, let's get to the end of this particle thing before I ask about plasmons and phonons.
You get a headache with this. In fact, I think it was Fermi who said, Enrico Fermi, who in the 50s said, if I would have known that they discovered so many particles, I would have become a botanist.
Yeah.
A collector. And another guy said, and I don't know which one said which, but another guy said, the Nobel Prize this year will go to the guy who doesn't discover a particle.
Yeah.
Because everybody was just discovering particles, and they were all equations. They were all wave functions. And they say, oh, here I see another particle. Oh, here I see another one. I'm going to name this one Charlie. I'll name this one Ricky. And so they just started naming these things and getting Nobel Prizes. And they say, what the hell is this? It just got, to be a Ptolemaic system.
Quasi-particles, plasmons, and phonons sound,
Yeah,
that was the straw in the back.
But look at the punch at the bottom. An important characteristic of bosons is that their statistics do not restrict the number of them that occupy the same quantum state. What do they mean by that? Two electrons cannot occupy the same quantum state according to what is it? The Fermi? No, the Fermi exclusion principle.
What's a quantum state?
They cannot occupy the same orbital, for example. They cannot have the same charge and be in the same orbital, and that's called a quantum state. It's got certain characteristics. And the bosons don't follow the Fermi rule.
So you can have two bosons in the same spot, same color, same everything.
Yeah, essentially you can apply the uncertainty principle, Heisenberg's indeterminacy, which says that the particle can be at two places at once, and two particles can be at one place at once.
It sounds like the program that I'm working on.
Yeah,
you have a bunch of things.
You can do whatever you want.
On each
as
other
long as you're dealing with concepts, you can put them in the same place.
Because that's how the game programming thing works. If you want to have 7 objects, you could have 7 balls all on top of each other. It just looks like one ball. They all occupy the exact same location.
Yeah. And but I don't think that's as weird. I think the weird one is when a particle can be at two places at once. Now you need a beer.
Yeah,
now at that point you need a beer to understand that one.
You can't even do that with the program.
No, not the same particle, right? You can only give it one location. I don't think you can even program that. I don't think God can do that.
That's literally impossible.
If God can be at two places at once, then we have two gods, and I think he would not like that.
You can have two. You can have two balls with the same properties.
No, do it with God. Two gods. Yeah. God would say, "How can I be at two places at once?" No, nothing's impossible.
By definition, if something is in two places, it's two different things.
They're
mutually exclusive.
Okay. Anyways, the good thing about a boson is that it's not limited by the Fermi. What is it? The
paradox?
No, the Fermi. What is it called? I just lost it. exclusion principle. In other words, that electrons can't have the same state, but a boson can. Okay, quantum state. So that's a good thing about bosons. You can have what this means. You can have as many as you want.
Do I even?
You don't have to account for them.
Do I even want to know how they came up with that?
I don't even think we can ever find out. I mean, they just can't account for some things, and they say, "Oh, we know what the answer is." It doesn't follow the Fermi exclusion principle. So that means they don't have to account for them.
They essentially say we can't account for this, so let's just say that's how it is.
Yeah, and see, that's why it includes gluons. Gluons, you don't have to account for them.
Yeah.
You can put as many as you want. Yeah. And same with the boson or with the Higgs. The Higgs, you don't have to account for them because the Higgs field is made of countless particles of actually, these they call Higgs bosons, and the Higgs bosons is a family that's together. It's like a field, a spread out thing, and you don't have to account for anything. So that's why they say, oh, it doesn't follow the Fermi exclusion principle. Period. We're done. And then we have the hadrons. You say, why is it called the hadron collider? Why is it not called the electron collider, the atom smasher, or whatever?
Atom smasher. That sounds like a wrestling name. I'm the atom smasher.
A hadron is a composite particle made of quarks, held together by the strong force, which is the gluon. The gluons are carriers of the strong force, in a similar way as molecules are held together by the electromagnetic force. So at the atomic level, it's the electromagnetic force, the photon, right, that holds atoms together, that builds molecules. But if you want to go deeper and you go inside the proton and the neutron, what holds them together, what holds the constituent quarks together are the gluons, the strong force. And hadron is a composite particle. In other words, essentially, it's neutrons and protons. Okay, that's a hadron. So whenever they say the hadron collider, they're colliding neutrons or protons. And they're trying to figure out what the quarks and the gluons that comprise them are made of. That's what they're doing. Okay, that's what's called a hadron collider. I call it hadron sometimes. I don't know why, but
yeah, some people call it hadron collider.
It seems like more natural. But anyways, hadrons are categorized into two families: baryons made of 3 quarks and mesons made of 1 quark and 1 antiquark. Okay, so we have 3 quarks.
What's
we have
an antiquark?
We have the up and down quarks. Those are the ones that make up the neutrons and protons. But then the mesons, they're made of 1 quark and the antiquark.
This actually sounds like the ramblings of a madman.
Yeah. Well, this is Ptolemaic. That's the correct term for it. It's a Ptolemaic. It's gotten so complicated. They've got all these epicycles, to say why does Mars go backwards? Well, this is how we're gonna explain this. We're just gonna put an equation in there that explains why it goes backward. We're gonna call it an epicycle. And these guys are doing.
We'll give it another one.
And these guys are doing the same thing today. This is the modern Ptolemaic system. They say, look, we've seen something new in the lab. What did you see? Well, this particle does this, has this. We'll call it a half spin. What do we call this one? That's a minus half. And that's a 1 spin. And this one has charge. That one has flavor. This one has, what's the other color? Well, what the hell? What is all this? It's a particle zoo. That's what it is. And, okay, so that's the hadron. And then we have the meson.
Wait.
Did I miss something?
Protons and neutrons are examples of baryons.
Yeah,
Pions are an example.
Okay, so let's get to the baryon first. Here's the baryon, okay? Because a baryon, well, here you'll see it. Baryon is a composite subatomic particle made up of 3 quarks. Okay. So the baryon is different than the meson. The meson is made of 2 quarks. The baryon is made of 3 quarks.
Oh, yeah, I got that.
Okay.
The meson is 1 quark and 1 antiquark, so you have 2, and the other one's 3.
Correct. 2 up and 1 down, or 2 down and 1 up.
Does that say if it's a proton or a neutron?
Yeah. Okay. Correct. And
are those the only 2?
Yeah. In other words, what they say, it's a triquark. And the other one's a biquark, I guess. It's I guess it gets into sexuality after that. Are you bi? Are you tri? I guess I don't know. Which are composed of 1 quark and 1 antiquark. Baryons and mesons belong to the hadron family of particles, which are the quark-based particles. Okay, so these are the quark-based, and again, all these subcategories and subcategories and so on. And okay, and finally we get to the fermion here. Fermion is a particle that follows the Fermi-Dirac statistics. So we have the Bose or Bose-Einstein and the Fermi-Dirac. Fermi means that it follows the exclusion principle, okay? That they're excluded, whereas the Bose or Bose-Einstein do not follow the exclusion principle. That means they can have the same quantum state. Fermi ones cannot. Okay, that's the difference between a fermion and a boson. Okay,
but just the question that comes to mind, I don't know if it's answerable here.
Yeah. It's not. Believe me, it's not.
How if two things are in the same spot, same color, same everything, how do you know that there's two of them there?
Well, because you don't have to account for them. The point here is that in the case of two electrons, they know that two electrons cannot occupy the same orbital. And so they say, Pauli exclusion principle. Those two electrons cannot have the same quantum state. They cannot have the same charge, the same orbital, the same, more than them. More than two.
Okay.
But then in the case of bosons, you say, well, how about the bosons? Oh, well, they can because we find unlimited numbers of them. So how do you account for that? If Pauli exclusion principle says you can, well, they don't follow the Pauli exclusion principle. They follow the Bose or Bose-Einstein statistics.
Okay, so the bosons, they do that in a way so that it becomes uncountable. Essentially, it's infinite because you could have, just like in the game program, you could have literally a billion spheres all in the same location, and it looks like a sphere. You don't know how many are there. I think that's why they do it, because if you have a particle there, right?
Yeah.
I mean, they're trying to explain the sea of particles, this field. So you have the sea of particles, but if it's a sea of particles, it's countable. It's, okay, there's a billion particles here. But they can't work with that because then it's
unmanageable.
No, it is manageable. If there's a billion, you can
count but you have what you have is a bottomless pit.
But that's my point. There's a difference between countable, if they can occupy, let's just take location because I think that's the big one.
Okay.
If they cannot occupy the same location, by definition, they are countable. By logic, they are countable.
Okay.
But if they can occupy the same location, then it's countless. It could be countless because you literally don't know.
Right, you can put as many as you want. You can put you don't know how many there are.
How many are there?
Okay, that's a different way of seeing it. The other way is, remember, the gluons is a sea. The gluon field. The gluon. Both. The gluon is a field also, but I was thinking of the Higgs. The Higgs is a field. What is a field? A field is a bunch of particles. The ether. It's a Higgs ether. And how many molecules are in the Pacific Ocean? Countless. We can't count them.
Countless.
Well, but they're saying it is countless in the sense that, well, where do all these particles reach? Well, they go to the edge of space-time. And where's the edge of space-time? It's unlimited. It's infinite. Yeah. So you don't have to count for the edges of space-time.
But it's not the edges only. That's my point.
The borders.
Forget the borders. With this boson, it's basically an accounting issue. If you can have two particles in the same spot, forget the borders. Even in the center of space, you can have infinite number of particles in one dot at one location.
Yeah, that I understand. That's good, because that means that what you're saying is that if you have a particle and that particle has a million or gazillions of particles in there that they can all occupy the same quantum state, or they don't follow the Fermi exclusion principle, then if they can all occupy the same state, then you don't know how many particles are in there, because one is superimposed upon the other, and how many are there? How many balls are there in there? We don't know, and so we don't have to. All we have to say is it doesn't follow the Fermi exclusion principle. We fixed it. And on the other hand, the other side of it, I think, is that if space-time is unlimited, even though it's not, because it had a beginning, but we don't know about the end, and maybe there is an end, the big crunch, Big Bang to Big Crunch, you can say that's the limit. But so far, when you ask all these people, they say, well, space is unlimited, space is infinite, and so you don't have to account for where the last gluon is. There is no border, according to them. It's like we're creating new gluons every day, or God is creating them. And you don't have to account for the whole shebang. You don't have to account for the whole sea, the whole cosmic ocean. That's the problem. The problem is people having an open checking account. They can issue as many checks as they want because they have unlimited amounts of money. They just create this stuff.
Was there something else that we needed to know about the fermions?
Oh yeah, let me finish on the fermions here for a second. We got sidetracked a little bit, but that's good that we cover those little details. These particles.
I want to know how crazy the fermions are. It can't be worse than the bosons.
No, this one is a little more irrational because these particles obey the Pauli exclusion principle. Fermions include all quarks and leptons. In other words, you have only 3 quarks inside a proton or inside a neutron.
Quarks. Okay.
And leptons are like electrons. You know, they have to follow the exclusion principle. That means there's a limited quantity of them. And God forbids 2 of these leptons from occupying the same quantum state. God has made it that. They don't know why, but it is that way. Okay, fine. But then it's the gluons, the Higgs, all the bosons. They don't have to follow the Fermi exclusion principle, and they follow the Bose-Einstein statistics, which means that you can have as many as you want, or like you say, I like that one too. You can have in fact, the picture we had yesterday of the gluon separating and turning into a quark.
That's what it is.
That's essentially
taking one out of the 2.
Yeah, and it's like they're superimposed upon each other, and they can create another quark if they want. You know, quarks are limited, but gluons, you can have as many as you want.
After the podcast, I can show you on the game program exactly what they're doing. I can show you. I can put a sphere on a sphere and then just move one sphere up, and then you'll be like, "Where'd that sphere come from? How many are there?"
It says, okay, fermions include all quarks and leptons as well as all composite particles made of an odd number of these, such as odd 3, right? Such as baryons,
not
the even ones.
The muons or the mesons.
Yeah, mesons, because those are 2, right? It's got to be the odd ones, the triquarks, such as baryons and many atoms and nuclei. Fermion differs from bosons, which obey Bose or Bose-Einstein statistics. A fermion can be an elementary particle such as an electron, or it can be a composite particle such as a proton. According to the spin statistics theorem, I like that spin statistic, all these terms they invent, theorem, in any reasonable relativistic quantum field. Now we have relativistic tied with quantum, right? Field theory, particles with integer spin are bosons. Well, particles with half integer spin are fermions. So if it only turns halfway, it's a fermion. If it turns a complete way, you know, one completely turn around or whatever, or they find it in a different direction, then it's called a boson.
Can quarks have half spins?
You got to look at the chart and find out.
I swear.
I'd have to, I'm getting a headache already.
That's what we need, but we need an actual scientist here next to us that we can ask questions to. You didn't go to the 4th year. You didn't get your master's degree, but I can't ask these things.
I mean, so let me go back to the beginning. Here we have the Ptolemaic system, okay? This is what we have for particle physics today. We have this Ptolemaic system of epicycles, so complex that they had to create all this nonsense with particles, because with particles they can't explain absolutely anything. Anyone who deals with particle is a retarded individual, and he should be put in prison.
But if
or in a nut house.
But they're not explaining anything. They're just classifying things.
Yeah,
it's kind of like a zoo. Well, you kind of said it right. If you see a monkey, it's like, oh, I call that a monkey. I call that an elephant. I call that a giraffe. You're not explaining anything. You're just calling.
You're just giving it names, and this is the issue. The issue is these people are not really explaining anything. All they're doing is using equations to describe these things. And describe again is a bad name because, like we said the other day, it's really a narrative, or what you're doing is describing motion, and we call that a narrative instead of description. Description, you describe a chair, something static, but then we got to use another word to describe something in motion, which is what an equation does. And what these people do is neither explain nor describe. What they're doing is, with an equation, they're describing motion, and let's call that a narrative. What they're doing is if you look at an equation, it gives you only 1 point. If you replace numbers in that equation for the variables, right? You put a number for that, you get only one result at a time. And now you put other values. You get another value, a number. You put other values inside the variables. Now you get another number. You plot these numbers. That plot is a trace of motion. That's what it is. You're having an itinerary. You're looking at the behavior of a particle or whatever they study.
Yeah, I like
there.
the word behavior.
Yeah, it's a behavior.
Behavior is by definition. I mean, it's by definition motion.
Yeah. So what these people do is equations do that. They just describe motion, and what I mean by that is, once again, the equation gives you only one value. If you replace all the variables in an equation with numbers, it gives you only one result, one value. And you plot that, 1 or 2, whatever number that you get. Now you put new values, you get another number. You put new values, you get another number. That trace, once you plot that, that's an itinerary. That's behavior of a particle. And that's what they do. And that's all that an equation can do. Equation has no power to explain anything. It can't tell you the cause of something, and that's why there are no rational explanations in mathematical physics.
But then
today.
it begs the question: what the hell are they doing?
Well, they're just having fun with numbers. These are people who are mathematically inclined. They come out of college or they go into college with mathematical orientation. They say, "Oh, I'm going to study physics." They call it physics. What are they doing? They're doing equations to describe motion. And they say, "Well, we can't see what a particle is, so we don't care about structure. We don't care about architecture. What we care about is how this thing moves, because that's all I can verify in the lab." Mm-hmm. That's why experiment, observation, prediction, and math have become science. Yeah, because that's all these people do. And then the problem is that they derive explanations, which are their personal opinions, based on the particle model. And they say, "Oh, see, this is how the universe behaves. We can tell you because we're excellent, we know math." But who cares about that? I mean, if you give me an irrational explanation, for how this universe works in the secret world of Mother Nature's, then who cares about your math, about, what you did? But see, they claim that because they can monitor the behavior of a particle, which they think is a particle, this invisible thing that they can't see, they say, since I can model it, then it kind of and we can make predictions that if we do this experiment again, the particle is going to have this squiggly line again, so we're going to call that a quark, or we're going to call that a gluon, or whatever we're going to call that. So because they can make that prediction, they say, we understand, we know how this universe works. But then you say, okay, how do you produce pull? That very simple question. Oh, we can't. We do it with a negative sign. Yeah, but that's irrational. Yeah, but the quantum world is irrational. We don't understand it. So
I love that answer. That's
so we're back to square one. We still don't have an explanation of how this universe works.
It's funny because like a couple hours ago, I saw that one video where they have Feynman or someone asked him how magnets work. And all the comments, were like, this is a very long-winded, I don't know, and things like that. Why didn't he just say
30-minute, like a 50-minute, I don't know. Yeah.
There were so many comments, and there are a few comments, obviously, with people like sniffing his ass and saying like, "Oh man, this is just such a genius," and those had all the thumbs up. But there were so many comments, you can tell that all the people who don't study that stuff are kind of just like, he didn't say anything.
Right. Essentially, and the other half, the one that said, "Oh, he's such a genius," because I got answers from some of those people. They say something like, "Well, he did explain it. He explained that we can't explain." In other words, that if you really want to understand it, you got to go to college and take a math course. Then you would understand.
Yeah.
It's like they're saying, he's a genius. I'm not going to take a course in college to understand. I'll trust Feynman. What he said, But
it goes back to this, where you have all these
irrational,
these words for behaviors that you notice in the lab. We call this one a mu. We call that one a boson. First of all, they're not seeing anything.
They haven't observed or detected. They use the word observe when they haven't observed.
Detective, maybe. They detected.
No, but they detect something.
Something.
The machine detects something visible. And they infer the invisible part. They never saw a black hole. They saw the sun, a star out there that's being twirled around. They say, there's got to be a black hole in. That's the inference.
Yeah.
And like dark matter, the galaxy rotates this way. There must be some mass out there, and we'll call that dark matter. That unknown we'll call dark matter. They can't see the dark matter. They can't see the black hole. They infer it. But they call those inferences, we've proven it. They say they proved it. I mean, you can't question black holes or dark matter anymore. Those are done deals. Those are already incorporated. They've been proven. They're not hypothetical anymore. And likewise, the Higgs has been proven. That's why they gave the Nobel Prize to this guy. And all these gluons and quarks, they have been proven because the guy already got his Nobel. You're not going to take it back and say, to Murray Gell-Mann, say, hey, give me, or Zwicky was the other guy, I think. Give me your Nobel back because there are no quarks.
Or
you can't do
you
that
didn't
anymore.
Explain anything.
No, they don't care about that. But once you show that there are no quarks, no such things as quarks, then you got to say, okay, give me your Nobel back. You don't deserve that medal.
Bad for science.
It's like the girl.
That's
It's like
actually a really good
the
point.
girl in Miss Universe when you say, hey, you're disqualified because you got false boobs or whatever. We're going to take that medal. In fact, it's the other way around. They usually give it to the girls with false boobs now. But you take the medal away and give it to the runner-up, and that's what they should do with these guys. There are no quarks. Give me the medal back.
That's a good point. It looks bad for science if all of a sudden
you can't withdraw all those medals.
If all of a sudden they prove, quote unquote, I hate that word.
There's too much authority out there.
I hate that word, but if they prove that black holes don't exist, they'd have to take back whoever's Nobel that proved black holes.
Yeah, Chandrasekhar. Chandrasekhar proved black hole. He got a black hole. He got a gold medal for a black hole.
That's so weird.
So what are you going to do with that? And Hawking never got it, but he became famous because of black holes. It's the same as Roger Penrose.
That's interesting. There's a difference between medals for science and medals for gymnasts.
Oh, there are? Oh, what's the difference? One is bigger? Or?
No. Because with gymnasts, they do a feat, right?
A what?
A feat.
Oh, okay, perform a feat.
A performance. They do something, and it's all timed and whatever. It's filmed, and that kind of stays in the past, right? What they did, they get the medal for that, and that can't really be retracted because it's a done deal.
No, they can. For example, the cyclist, medalist. I can't remember his name now. They took his medal away because he was using.
Okay,
he was doping. No. But the point is, they can go back and take your medal.
Yeah, but I'm saying there's a difference because
they amend the record.
Yeah, but that's just because he was cheating. But that's not what's going on here.
So this is cheating too.
That's not what's going on here.
Oh, it's not cheating.
Because here it's more like
this is cheating.
The theory you come up with is for the future. From this day onwards, we're gonna take your theory. That's what that means. But then you're kind of putting your money where your mouth is from now. If anyone okay, that's the question. Has anyone ever proven a Nobel Prize winning theory wrong?
Impossible. That's my point. I mean, have we proven phlogistons that existed in the Middle Ages and Renaissance or whatever, about the 17th or 18th century? They came up with this phlogiston. They came up with ether. And have they proven the ether wrong?
But did they
but no, they just modified it. Einstein called it space-time. These guys call it the Higgs field. It's always the ether, but it's like this Nobel Prize guy said. He says, Einstein's space-time is an ether, but we don't call it that because it's taboo. You can't use the word ether anymore. But it is an ether. They need this field concept. Without the field, they're dead. And so they had to create the field concept, and the field is ether. That's what it is. Because a field is conceptualized as a whole bunch of particles. And particles don't work.
Yeah, back to this particle zoo thing. What is their end goal? Like if I were a scientist or a mathematical physicist in the lab or wherever they do their thing, naming these things, like what is the end goal? Just to give a name to every animal in
that's
the zoo?
A good question, but there's two answers to it. On the one hand, they're trying to what they're trying to do is get to the particle that the one and only particle that makes up everything. That's on the one hand. That's why we need more money. We need bigger atom smashers to find
the real fundamental one.
To get to the fundamental guy, the one that makes up everything else. But they say we don't even know if there exists such a thing because right now they have all these fundamental particles, there's several of them. The electron is one of them. They can't figure out what the electron is made out of. Photon is another one. They can't figure out what that's made out of. So they say, we can't smash a photon and find out what the sparks are made out of that come out of it. So that's on the one hand. On the other hand, you have a contradiction. You have a contradiction because quantum mechanics demands that there be a fundamental particle. You can't continue breaking up the onion and breaking up and always finding two, and two, or three or four, more. You should at some point get to the seed of the apple. You should finally open the apple and say, this is what makes up everything else.
You can't break that one down anymore.
You're right. There should be, but then once you get to that one, the reporter in the crowd said, what is it made out of? Well, we need more money to be able to smash it and find out what it's made out of. So we're never going to get, because it's an endless quest. Particles made of particles made of particles made of particles. And so you'll never get to the bottom because people say, well, what is it made out of? You can't, they don't respect their word elementary, or they don't respect their word fundamental. They called it a fundamental tentatively.
It's like the Russian dolls that there's always the Russian doll and the Russian doll and the
Yeah. You open it up and there's another doll in it. Yeah. And this is the same thing. The word fundamental is meaningless in quantum mechanics, and the word elementary is also meaningless because elementary is a tentative. It's for now. Tomorrow when we break it up, we'll find that it's made out of something, and then somebody will ask, what is that one made out of, and so on down the line. We'll never get to the bottom of it. We'll never get to the center of the onion.
The universe works in mysterious ways.
Yeah, and there's a third part to this. Third part is that now we have unlimited science. Science is not finding, science is seeking. You seek. You have job security forever because we're investigating. We're breaking. We're still investigating. We never get to the bottom. Our theories are not the end point. Our theories are all tentative because tomorrow a new theory may come along.
It's like the adventure that never ends.
And what are they talking about? They're talking about not theories. They're talking about accuracy. Right. They're saying, I'm going to get an equation that describes this a little more accurately than you. Like Einstein described, gravitation at the macro scale more accurately than Newton. So Newton was pushed aside. And they say, well, Einstein's more accurate by a millimeter. He's a little more accurate. And it turns out that NASA doesn't use Einstein. NASA uses Newton. And they say, well, Newton works just fine, for us. And Einstein's too complicated. We love Einstein, but we're going to use Newton. They use Newton for everything. They use Newton for rockets. It's force equals constant g, mass divided by distance squared. That's what NASA uses. NASA doesn't use the nonsense that Einstein invented, which is the itinerary of a point mass. And that's important to note because, these guys have to talk about escape velocity. For that, they can't use Einstein. We're going to stay with 17th century Newton. That works just fine for us. It's much easier. Mass times mass divided by distance squared. We can all deal with that. And the other stuff is too complicated. That's good for the physicists over there in Cambridge. They can do all their stuff from over there and work with Einstein. And that's the problem. And these guys are the same thing. These guys are just looking for equations. They're looking for more accurate. What is string theory? Equations. And they're trying to find an equation that can unite general relativity with quantum mechanics. They have the quantum world, the world of the little, that has these fields, and it turns out that Einstein also talks about fields, and they say, well, we got field here, we got field here. Let's see if we can get an equation that can unite the field of quantum with the field of general relativity, and that way we quantize space-time. The event, which is a point in space-time, gets now quantized. We get to look at what happens inside an event at the particle-to-particle interaction.
This sounds a lot like Peter Pan syndrome.
Oh, what is
where
I heard of that,
they don't. I mean, I'm interpreting it like this, where they don't want to get the answer. They don't really want the grand unified theory, because then physics is done.
In a way, that's true.
They always want whatever answer you come up with, if the more questions we have about your answer,
the more job job security.
If your answer answers it perfectly and we don't have a question, you just killed it for so many people. Right. Now you basically ruined it. So you ruined the party. Like, oh, come on, dude, we were having such a good time just trying to understand all this. So they don't want to get to that point where we know everything. They don't want to know everything.
You have two counterpoints on that. One is that there are a lot of people out there, and I'm not just talking about ordinary people. I'm talking about physicists or mathematical physicists, and they say it's the end of physics. So some see it as a beginning. We got a million questions to answer, and the other guy sees it as an end. Like, we're not answering any questions.
Oh, is that how they see it?
Yeah. So there's a lot of people out there that say it's the end of, and you'll see, if you look up the end of physics, is it the end of physics? You'll look at words like that in Google. If you Google it, you'll find a lot of people say, it's like the end of physics. What are we doing?
But because they see all this particles,
right, and they're starting to question. They're saying, "Look, all we're doing is just getting into this part and just giving you more names and saying, well, this one has half spin, the other one has positive spin, this one has negative spin, this one has charge, this one has color, flavor, and so on, And so they get into, they're just naming things because they're just giving more properties to these things. Say, well, hold it, this one is a little different than that one. Well, the difference is the color. And this one, the difference is the flavor. And this one, the difference is the spin. And so they have to recategorize all these things because they go to the lab, they see all these squiggly lines. They say, well, what are we going to do with that one? Well, that one's got a different flavor. Well, and what about that one? That one's got a different color. And so they have to come up with all these nonsense names and properties.
It comes down to the fundamental problem with a lot of jobs where the better you do the job, the faster you're out of a job.
Yeah,
it's
and you
can't
like
do that with science, where the whole point of science is to
understand.
Have an end, is basically to so that there's no more scientists.
Yeah, to work yourself out of a job.
Yeah, that's basically the job description. Yeah. Answer the question and then go do something else.
And the worst thing you can do is work yourself out of a job. So how do you do that? Well, you say, well, we don't find, we seek.
But I think it's not a conscious thing. I think
we're always on a quest.
But I think it's more like a something done in practice, not really a conscious thing. It's not like they're trying to avoid answering questions. It's not like that. I think it's more like a subconscious kind of like done in practice kind of thing. It's more subtle. But my question is, if there were a grand unified theory, for example, like your rope hypothesis, they came and just answered it, what do you think would happen?
No, it would be the end of physics. Then you could say, oh, now it truly is the end of physics because now we know how the universe works. And there's another issue based on what you just asked. Also, it's that you've got the issue that people are not getting their questions answered in a qualitative way that they can understand. And so the people keep asking the same question from different angles. Look at Quora. They ask the same million questions from different angles. And they're trying to figure out, what are you talking about? How, let's just, as an example, gravity. How does gravity work? And they give you this long-winded answer about, equations and how Einstein was more accurate than Newton. Okay, great. And then another guy said, well, yeah, I still don't understand. Why doesn't the Earth go flying out of the solar system? Well, because of this and that, because space is warped and there's a depression and so on. And you say, but is space-time a physical object? And they say, well, for this you got to go to college, see, because we cannot really present in a qualitative way our mathematical equation. So they give you this runaround and people come back and the next generation comes back. What is space-time? How does gravity work? They keep asking the same stupid question over and over. It's never ending. And the mathematicians don't know how to tell them, look, if you want to know, take a college course. Don't ask me, because I can't tell you, like Feynman said with magnetism, I can't tell you in a straightforward way, like in baby talk, how a magnet, the simple system,
you're gonna have to do that again. I missed it.
Yeah, I mean, you can't. I mean, that's as simple as it gets. This is the entire system. I mean, do I have to take a college course for this to understand how one piece of metal attracts another? All I need to know is what's in between them. That's all I need to know. And of course, there's these retards out there that say that something is pushing the magnets together.
And that could still be it. I'll take that over particles throwing negative.
Well, you have particles. Here I have the two options. I like those two options. So with particle, no, but we got to finish with this thing here. Let me get it here. I got it near there. And the other one is what? Where's the other one? Where is it? Oh, here it is. Here are the two systems with particles, because you have no other option. Here's the particle one, and here's the pressure one, the one with the one where you have Casimir, being pushed from the sides. So those are the two mechanisms for gravity.
Every time I see that, I have to laugh.
Yeah, because
Donkey's just like, why are you throwing rocks at my face, bro?
Yeah, so
cool.
That's the particle model. So anyone who talks about ether or particle, he's got to have his head stuck in the toilet, because he doesn't have a slightest clue of how the universe works and will never be able to explain it rationally. If you want to explain pull, you got to have an elongated medium between the two objects. And you don't throw rocks, and you don't remove matter from between them, or any other mechanism that you can think of. I don't care. You just can't use pressure to push two things together, because how far in the universe are you going to go? Are you going to go all the way to the edge of the universe and say, well, what's pushing the last particle in? I mean, how far do you want to go? To the edge of the universe? And of course they make it infinite so that you don't have to account for the edge of the universe. They say, well, the universe is infinite, and so we have infinite particles, and they're pressing. So here these guys are saying, that this is being pushed together. These two magnets are being pushed together. That's what these idiots say, the ether and particle people, because the particle people are also field people, and field is a bunch of particles. That's what it is. And they say that this is being attracted to that because something is pushing from the outside, or because there's negative momentum from the inside, a field. And again, it's retarded. We should get rid of the particle model once and for all.
I wish they'd just say, I don't know.
Yeah, that's essentially what it is, Anyways, folks, we'll see you tomorrow, same time, same station, and we're just going to wrap it up also for the particle world. Ether, anything that comes to my field, the Higgs field, the ether, the space-time field, the field of fields, the poppy field, the football field, whatever field. The football field is made of spectators. That's what a football field is made.
Yeah, whatever questions you can come up with, just come up.
And all the spectators, they compress each other, and that's why we're pushed together. That's how pull works. Okay, we'll see you tomorrow.
To have more questions in the chat.
Okay, we'll see you tomorrow. Same time, same station. Bye bye.